So then let me start. First of all, thank you very much for the kind invitation. It's a pleasure for me to speak in the seminar. And actually, for some of you, it's Carnival today, as we have it here also. So I nevertheless try to give a serious talk. And if there are questions, please interrupt me any time. I will talk about species, their thermodynamics and emergent strengths. And in fact, this is a joint work with Ivano, Nicolo, and Carmine, appeared in 3 papers. I think you can see the 3 nice people there. And with that, I like to start. Here's a short outline of my talk. I will first introduce the species in the species scale. Then I will discuss their relation to minimal black holes as species-bound states. Then I will switch to so-called general species towers in the emergent string conjecture. And finally, I try to summarize my talk. So let's start first with the species in the species scale. So what are species? Species are in general some particles that can be light in the effective field theory. They are assumed to interact gravitationally. And otherwise, we will assume that they are weakly interacting. Species turn out to be very important for the fundamental understanding of quantum gravity. They set the scale, the cutoff scale of quantum gravity, as we will see, that is a so-called species scale. They appear in the so-called swampland distance conjecture, namely light species appear at large distances in the moduli space. And as I will discuss, they have also a very interesting relation to black holes. And therefore, they will also, as we will discuss, possess a thermodynamic nature. Moreover, species are also very important and interesting for phenomenology, both in particle physics and also in cosmology. I think one of the first appearances was to solve or to propose a solution for the electroweak hierarchy problem. And there's one interesting scenario in this context, namely the 10 to 32 copies of the standard model, which was introduced by Dvali and Reddy. And I think there's also very interesting recent work by people here in our institute, Manuel Ettengruber, Zander, and Eller. Next, they are also possibly important for the cosmological hierarchy problem, appearing in the so-called dark dimension. Namely, it was argued that if the cosmological constant becomes small, there also appear light species in the effective field theory. And finally, they were also recently introduced as candidates for dark matter. So you can see there's a wide field of interest in species these days. And in fact, as I have mentioned already, they are relevant and important in the so-called infinite distance conjecture. I don't have to really introduce here in this audience what is the infinite distance conjecture, but let me just show it very briefly, pictorial to you. We have a quantum moduli space, which is parameterized by some scalar fields phi. And at certain infinite distance limits in the moduli space, we expect to have a tower of states whose masses scale with the exponential of the distance in field space, as it was proposed by Hiroshi and Komrun some time ago. Now, a refinement of the infinite distance conjecture is the emergent string conjecture. It was proposed by the 3 gentlemen you can see also here on the screen, Lee, Lerche, and Weigand. And it is claiming that there are only 2 kinds of towers which can appear in these infinite distance limits, namely only 2 kinds of species. And they're either given by light string excitations, so light string modes, so-called tensionless strings, or light KK modes, which signals a decompactification limit in moduli space. So I think this conjecture is very important because it addresses the question whether string theory is the only theory of quantum gravity in some way, or whether there are also alternatives to string theory. So it is also posing the question of the string, so-called string lamppost. Now in this talk, I will actually address 2 questions. Namely, the first question is about the entropy of particle species in quantum gravity. And to be specific, we want to ask the question, is the entropy of this particle species extensive? So does it follow a volume law, as you would expect from particles in quantum field theory, or does it follow an area law? And moreover, does it follow some universal thermodynamic laws, as we are used to have them also, for example, from black hole physics? The other question is whether we can shed some more light on the emergent string conjecture. And in fact, I think it's fair to say that so far, many very successful top-down tests were performed in string theory. So there's a very good evidence in string theory for the emergent string conjecture. But I think some general bottom-up arguments, for example, from black holes are still missing. And I think that would be really also very important to know, because in this way, we could argue whether the emergent string conjecture is true in a generic theory of quantum gravity or whether there are alternatives. What I will argue today is that species thermodynamics will indeed help to provide bottom-up evidences for the emergent string conjecture. So this will be basically the main theme of my talk. So the species scale was introduced, or not introduced, was discussed by many people, by several people during the recent years. You see some of the faces here. I'm sure I have also forgot some of the recent contributions, so I'd like to apologize for that. And actually, the species scale, as we deal with it now, was introduced first by Dwali in the year 2007. I think this is a very nice observation. The species scale can be defined as follows. Usually we will use Planck units, but here I have also spelled out the Planck mass. So in a d-dimensional effective field theory, the species scale is given by 1 over the number of particles, the number of species raised to the power of 1 over e minus 2. So as I just said, n species is the number of particles below the cutoff, as you can see in this picture. And in fact, this definition should hold regardless what are the masses of the particle species. So it just counts the number of species, but it also, in a little bit more hidden way, depends on the moduli fields, because the number of particle species also depends where you are moving in the moduli space. So lambda species, as it was emphasized also recently, is indeed a quantity which is varying over the moduli space. So this is the original definition of the species scale, which turns out to be very useful and very nice. More recently, the species scale was defined in a little bit more general context, namely as a UV cutoff in EFT quantum gravity. So it can be regarded as the shortest possible length in an EFT. One way to see it, and this is basically the definition or the way to see it, which we will use also in the following, is that lambda species is a scale where gravity becomes strongly coupled. But as I just said, there's another also very nice way to introduce the species scale. I call it lambda UV. That is the mass scale where higher curvature operators in the effective field theory become relevant. So indeed, if you set up an expansion in terms of curvature invariance, so in a way it's a momentum expansion, you see that the terms which appear in this expansion are not suppressed by the Planck mass, but by some, in general, different mass scale, which we call lambda UV. I think this is the way how it was proposed by the Harvard group. And in general, indeed, one would expect that this scale lambda UV is the same or is of the same order than the species scale, which I have introduced before. But as we will see, there can be also subtle differences between lambda UV and lambda species, which I will discuss.
Sorry, can I ask a quick question?
Sure.
So one very nice case would have been that the higher derivative terms are suppressed by KK scale, right? If you get the gravitational term by integrating out a KK tower, shouldn't you expect that it's suppressed by KK scale?
It depends what kind of, I think, scenario you're looking. So they can be suppressed by the KK scale, by the higher dimensional Planck mass, if you wish. But I think there are other ways. And I think this was also investigated in some detail in some papers, which whose authors appeared on the previous slide. So it depends really what kind of state you're integrating out. Can be also string states. And I think then it also depends what really we mean with lambda UV. Maybe we will come back to this question also later on.
Okay, so but I should think of lambda UV just being the of these terms that you have in this equation to be purely gravitational terms or any kind of term.
At the moment, I have written it in gravitation terms, but there are also other higher order, higher momentum operators, which could also include some gauge fields. So in principle, also lambda UV could also appear in some higher order gauge terms or even mixed terms, mixed gravitation and gauge terms.
Okay, thank you. Thank you.
Okay. So let's come back to the question, what is the species scale in terms of strongly coupled gravity? And one alternative definition of the species scale, which is of course also closely related to the previous definitions, is that the species scale or the inverse species scale corresponds to the radius of some so-called minimal black hole solution of some minimal black hole in the effective field theory. That was also proposed by Dvali and Reddy some time ago, and we also recently investigated this proposal in some more detail. So the idea is that the effective field theory allows for black hole solutions, but they cannot be arbitrarily small. Their minimal size in some instances is not given by the Planck length, but by some bigger radius. This is a so-called radius of a minimal black hole. And this we can also use as a definition of the species scale. So again, I depicted this in this picture. We have some species, some tower of states, and they correspond or even they build some kind of minimal black hole. But the question is this possible for any kind of species, or what towers indeed correspond to a minimal black hole? I think this is an interesting question also to ask. So let's assume that there is such a minimal black hole which is setting the species scale, and this can now, from the minimal black hole perspective, can be used to get a nice definition of what we mean by the species entropy. Namely, the species entropy is just to be defined as the entropy of the associated minimal black hole. So what we call the species entropy is precisely this entropy. And if you use a standard formula, if you use the standard area law for the black hole entropy, you get this species entropy is given by lambda species to the power d-2, which just corresponds to the area of the minimal black hole. In the same way, you can also try to introduce a species temperature. And again, the species temperature is then defined as the temperature of the associated minimal black hole. So given by the inverse radius of the black hole, or the inverse radius of the species scale, and so lambda species, L species to the -1, which is nothing else than the species scale itself. All right, so these are the two definitions of the species entropy and the species temperature. And we will also see whether they make sense later on. What we then also want to require is that the species entropy and the species temperature follow the known and the standard laws of so-called black hole thermodynamics. Now we can, in a way, again, rewrite or refine the large distance conjecture. We call it here the black hole entropy conjecture or the species entropy conjecture. And it would is now saying that in the limit of large black hole entropies, there is again a light tower of states whose masses scale in this way. This is what we proposed some time ago. Or then applied for the minimal black hole, it would mean that the associated tower is then given in terms of the species in questions, and the species in the black hole entropy corresponds to the species entropy. So in the large species entropy limit, where a species goes to infinity, we get a tower of masses, a tower of states, the species themselves, who also scale with some particular power gamma with the inverse species entropy.
Can I ask you a question, Peter?
Sure.
So when I have a very large black hole, the horizon size of the radius of the black hole is going to 0. So that's the Kaluza-Klein scale of the S2 of the black hole, right?
Right.
So that Kaluza-Klein scale is going to 0. Would that be an example of the tower that you're talking about?
That would be an example of the first tower where we consider an arbitrary big black hole, not necessarily a minimal black hole. But if we then specialize to the so-called minimal black hole, then the claim is that this tower is precisely the species tower, which we have in mind, namely the particles, the species particles in the effective field theory under certain conditions, which we will discuss in the following.
One question also.
Yes.
Here, the limit in which you're sending the mass to 0, you, for example, in a compactification limit, you would have that the compact dimension would grow. So would this entropy of the smallest black hole that you are computing could be like in the lower dimensional theory, or also considering that you are growing the internal dimension?
This is a good question. We are always considering the entropy of the minimal black hole from the perspective of the lower dimensional theory, because we are measuring any scales in terms of the lower effective of the lower dimensional effective Planck mass. Okay. Any other question here?
Sorry, can you hear us? Can you guys hear us? Yes.
Yes, but please speak loudly.
So just to make sure we understand what you mean by this. So you're saying what are you tuning when you say I'm going to take a large black hole entropy? You're not changing the moduli of the theory.
Indeed, if we move, I told you before that the species scale and therefore also the species entropy depends on the moduli, because the number of species also depends on the moduli. So indeed, what we have in mind, what I have in mind, that indeed I go to some infinite distance limit, into some infinite distance corner in the moduli space, where the number of species grows, becomes large. In this way also, the area of the minimal black hole becomes large, and therefore also the species entropy grows.
So when you say S black hole goes to infinity, you don't mean a very big black hole. You mean go to a corner in the moduli space. Go to some boundary in the moduli space.
I mean, the species. The minimal black hole is some kind of limiting black hole. You cannot construct any smaller black hole in the EFT than this so-called minimal black hole. And since the species scale is setting also the cutoff, it is natural to expect that these two scales agree with each other.
Is the scale of the minimal black hole much bigger than where you expect Gregory Laflamme to kick in and the black hole to be unstable?
It depends really what kind of black hole you are considering. Of course, the black hole might decay via possibly also via Hawking radiation, and maybe one has to also compare the decay rate of the black hole. But this is at the moment not the issue. I mean, the correspondence between the species and the black holes, as I will say in a second, is in a way a little bit formal, but there is a clear one-to-one correspondence between certain types of species and this so-called minimal black holes.
Thank you.
Okay. So indeed, this is what I tried to explain before. We have this quantum moduli space, we have a tower of states, and if we go to infinite distance limit, the number of particles, for example, the number of KK modes becomes large. And in this way, also the species entropy becomes very large. And at the same time, also, if we have a kind of Schwarzschild minimal black hole, the species, the so-called species temperature, becomes very small. Okay, so let me try to say a bit more what we mean with these minimal black holes, namely the minimal black holes as species bound states. Here again, formulation of Iyad Wali and Cesar Gomez, I think is very useful. It is a so-called n-portrait picture for black holes, which describes black holes as bound states of a certain number ng gravitons. We don't need to know the details of it, But if you work out at least the scaling relations, it turns out that the black hole radius now of an arbitrary black hole, which is composed out of ng gravitons, scales in this way. It's the number ng. The black hole entropy in particular is just proportional to the number of gravitons ng. The black hole temperature is given by the inverse Schwarzschild radius. And the black hole mass is given in terms of this particular power ng with a power d-3 over d-2, just as it is the case for standard Schwarzschild black holes. So in this way, these black holes viewed as graviton bound states, they follow the known general thermodynamic laws. The entropy is given by the area law. In terms of the mass, the entropy is given by this expression. And the same is true also, similar relations also hold for the temperature. And these relations will turn out to be very, very important for us because they are in a way connecting mass, entropy, and the temperature of generic black hole solutions. And in fact, they stem or they are consistent with the so-called first law of black hole thermodynamics, that the variation of the black hole mass is given by TdS, and the temperature, or the inverse temperature, is given by the derivative of the entropy with respect to mass. So these are the well-known thermodynamic relations as we know them from black hole physics. So what we can now do, as we considered some time ago, we can introduce, in addition also to the gravitons, a certain number of species, of massive or light species. And then, as one can show, the relations which I have shown you before are modified in a way that basically one can replace in a little bit, not really heuristic way, but one can replace the number of gravitons by the total number of particles, which is here given by the product ng times n species. So we again recover the same kind of relations before for the black hole entropy, for the black hole radius, for the temperature, and for the mass. Everything is now expressed in terms of the product of ng times n species. And then the final step to get a so-called minimal black hole, one can simply set the number of gravitons to 1, such that the total number of, if you wish, constituents of the black hole are dominated by the species. And then what we get is a so-called minimal black hole. We start from an arbitrary black hole, which looks kind of big, and we reduce successively the number of gravitons, and finally we arrive at a minimal black hole where the ingredients or the constituents are only given by the blue dots, and this is what we would then view as a minimal black hole. So this, in a way, is kind of suggestive. It again suggests that the species entropy now, it is given by the entropy of the minimal black hole. It is simply given by the number of species. The species temperature is given by the number of species in this way, and the species energy, which is the mass of the minimal black hole, is given by this particular power of the number of species. So this is kind of perhaps still a little bit heuristic picture, which you would get if you introduce the minimal black holes in this way. Perhaps one should not take this picture, I think, too literal. What I would maybe better propose is a kind of a dual description. We have some certain, in general, some certain particles, and there can be dual to some kind of geometry. And here, more specifically, we have these species as particles, and they correspond to some minimal black hole, which can be viewed perhaps as some species bound states. Or if you wish, maybe the more accurate description would be also that there is a transition between the particle and the black hole description. And in fact, at a large number of species, the black hole picture is possibly more appropriate. So for large entropy, we have a collective black hole description, and for small entropy, the description, the individual description by quantum mechanical particles is more accurate or more appropriate.
So, Dieter, can I ask you a question?
Yes, please.
So they say that for small entropy, this description as quantum mechanical particles. An example of this transition is when you have perturbative string theory, you have the Polzinski-Horowitz transition, where you have more like a gas of strings.
Yes.
So is that covered? Is that including what you mean by quantum mechanical particles?
Yes, it is precisely covered, and I will elaborate on this string black hole transition a bit more in a few slides. Indeed, that's what we have in mind. But what I like to really emphasize is that if this picture makes any sense, it means that the black hole laws, that the thermodynamic black hole laws must be fulfilled. Only in this case, as we say, the species black hole correspondence works. And if you write this out very simply, it means that the species entropy must be given by the species scale to the power of d-2, and the species, this total species energy or the species mass must be given by this particular power of the species scale. And as we will see, these simply and innocent looking relations will in fact put rather strong constraints on the kind of species for which such a correspondence possibly holds. Okay, so now let me generalize this picture. So far, I have mainly talked about these black holes as bound states of species. And now I wish to give you a more like a microscopic picture, or in other words, I like to introduce general species towers. And in fact, I like to come back now also to the emergent string conjecture and its connection to the species entropy and to the species thermodynamics, as we have discussed it or introduced it now. So I will start with a very general ansatz for a species tower. So I have a certain mass spectrum, Mn, which is given by some typical mass scale, little m, that is the tower mass scale, and then some a priori very general function, f of n. I assume it to be discrete, and this number n goes from 1 up to some capital N, which we will determine also in a moment. And I also like to allow that at each mass level there can be a certain degeneracy, which I denote by dm. So this is a rather, I think, rather general starting point, or rather general ansatz for the species tower for the particles in the effective field theory I have in mind. Actually, this tower mass scale m is the quantity which is in general moduli dependent. As we will see, this m can be the kk mass scale or the string mass scale, and as we know, this in general depends where you are in the moduli space. Okay, so what is now a good definition of the species scale in this context? Actually, we define the species scale, or we like to regard as a species scale, the highest, the most massive particle in the tower. So the species scale is given by the mass scale m of capital N. So in fact, here I have a little typo in my formula. This should read m times f of capital N. So this is basically the end point of my tower. It is the highest end of my tower. The species number are just all the particles in the tower, which means that I have just to sum the degeneracies at each level, and this gives me the species number. And for the species energy, I also make a kind of maybe a little bit simple, but I think still good definition, namely the species mass is given by the sum over all the masses in the tower. So I just sum up the masses of the tower, including the relevant degeneracies. So in a way, I assume for the species energy, that there is no binding energy and there's also no kinetic energy. So in a thermal bath, there are basically no thermal fluctuations, which means that I also assume in some way that the temperature, the corresponding species temperature is low. And I think under these assumptions, I think this is also a very good definition of my species energy.
One question.
Yes, please.
If you're still considering like the species energy is the mass of the smallest black hole, would it happen that that smallest black hole is composed, but not like one of each different species, but I don't know, like mostly the lightest ones or something like that?
I will tell you, I maybe answer this question later on, because in fact it will be just the opposite. The minimal black hole will be dominated by the heavy species, taking into account the degeneracies, but not by the lightest one. But in fact, indeed, that is what I have in mind. My minimal black hole is just a composition, a bound state, if you wish, of these species whose general spectrum I have introduced here. That's correct.
Okay, but maybe how do you know that that's like the smallest one?
I don't know it yet, and indeed I will now formulate the condition for such a tower to be able to form a smallest black hole. That is precisely one of the relevant questions you are also asking. Now, at the moment, I don't know it, but I will formulate some conditions that this tower at least can form a so-called minimal black hole. Correct. Okay. So this is my starting point.
Okay.
And
So
other questions?
Yeah,
there was another question.
Yes, please.
So here, at this stage, where everything seems very generic, what is fixed in capital N for you?
Capital N, in a way, is a little bit given implicitly. You will also see it. If we express the species scale in such a way, I think it will become clear in a second. You can also take this as a definition for capital N, namely it is given by the species scale in this way. So the definition of lambda species and N are not independent from each other. And maybe it will become more clear in an example which I will present you in the following.
Okay, thank you.
Okay, good. But first, again, without any reference to black holes or to minimal black holes, we can also now try to compute the species entropy, the so-called microcanonical species entropy. It is given by some partition function, which is a sum over all the possible degeneracies, d of m weighted by q to the m, where q is some kind of fugacity. M is now dimensionless mass scale. It is the species mass divided by the typical power mass m. So m is a dimensionless number, and you can rewrite this partition function in this way. So where we sum over all the mass levels up to n with this expression 1 over 1 minus q raised to the masses, and with the power of the relevant degeneracies. The inverse of this formula gives you the dm, some certain circular or contour integral, and then the microcanonical entropy is just given or just defined to be the logarithm of this total degeneracies of states, or in other words, the entropy in this way can be computed in a concrete example via a subtle point approximation, and basically counts the number of multi-particle states that build a state of a given mass, capital M. And as one can see in many of the examples, this degeneracy D, or the species entropy, is then related to the number of partitions, namely of M into N species parts, as it was also pointed out in this paper. So, but in a way, it gives you a very rigorous and in principle computable way or definition what we now mean by the species entropy. Okay, so Let us test this proposal by with some of the known towers which actually appear in the infinite distance conjecture or also in the emergent string conjecture. In the first example I like to take is a kind of standard KK tower. So how does a KK, a Kaluza-Klein tower, look like? The mass spectrum is given by some integer little n raised to some power 1 over p. The species mass scale is nothing else than the Kaluza-Klein mass scale. And for this kind of isotropic KK tower, we take the degeneracies to be constant, to be 1. And as one can convince oneself, this number 1 over p is just a nice way to count the number of compact dimensions. So p basically denotes the number of isotropic compact dimensions. So p stands, for example, for a p-dimensional torus from which we compactify to our d-dimensional effective field theory. So this is the starting point.
And
now
can I ask you a question about this case?
Yes, please.
If I have an n-dimensional torus decompactifying, I would say that the dn should be something like the number of integer points with a given norm, right? So that's definitely not 1.
I agree with you, but for large n at least, we have chosen a clever parameterization. I think this was also first introduced by a paper of the Spanish group. And indeed, we can discuss this. You can reformulate the tower, or you can rewrite the tower that indeed at each mass level, it has degeneracy 1, and the degeneracy comes precisely from this power of 1 over p here.
Okay, thanks.
So as you can see, the power, if p is bigger than 1, becomes denser and denser if we go to higher and higher states. So now you can use the formulas I have provided you before, and after some little algebra, you see that the number of species is given by this expression in terms of mkk. The species scale is given by this particular expression, and this basically reproduces the known formula for the species scale and the species number for this kind of KK tower. Next, you can also use the microcanonical entropy formula, which I have given you before. And then you see that with some corrections, indeed, the species entropy is given by the number of species multiplied by this particular number. Actually, I'm not sure if you can also see my arrow, my cursor, when I point to some of the formulas. So the species entropy is given by n species to the times p plus 1 over p. And this precisely also satisfies one of our required thermodynamic relations. And finally, you can also sum up the tower. You can sum up all the tower masses. You get some particular nice function. I think it is a Hankel function in this way. And if you approximate it, you see that the species energy is given by the species scale raised to the power 3 minus d times this particular prefactor p over p plus 1, again with some correction term. And indeed, it satisfies the required laws of species thermodynamics. So indeed, to address one of the questions asked before, this, from our point of view, is a good tower. It's a tower which indeed corresponds to a minimal black hole because it satisfies the black hole thermodynamic laws which are required in order to be able to form a black hole. So this is the first top-down example which I'd like to show you. I can also now continue and go to the okay, sorry, before I do this, I'd like to make some more remarks. As I just said, the thermodynamic black hole relations are satisfied. So the KK species indeed can build a minimal black hole. And indeed, for the KK tower, the species scale agrees with the UV cutoff. Namely, what is the UV cutoff in this scenario? It is nothing else than the Planck mass in the higher d plus p dimensional theory. And if you analyze certain, in the way I introduced before, certain higher dimensional operators, this is nothing else than the UV scale, lambda UV. And indeed, here it nicely agrees with the species scale, lambda species. And in fact, one other observation, I think, which is I think well known, is that the KK tower, all the KK states which we are summing up, are always light compared to the UV cutoff scale lambda UV. All right, so this was a KK tower, and the next tower I'd like to analyze in a little bit more detail. Again, still from the top-down perspective, is a string tower. So for string scales, we have this particular spectrum. The typical mass scale is given by the string scale, and now the degeneracy is not anymore constant, but in fact is given, is exponentially given. The degeneracy is basically by e to the square root of n divided by square root of n, or in other words, e to the energy divided by the energy, by the excitation energy of the strings. There's one, I think, nice way to view the string tower, namely can be regarded also as a KK tower, where you take T very large, but this is in fact not the way I like to consider the string tower now. I like to stick to this definition. And again, we now can turn on our machinery, and if you do this, some, yes, I would say some small surprises arise. If you now compute the species scale, it turns out it is not precisely given by the typical mass scale, the string scale, but it is corrected by a factor log of 1 over ms. So the species scale is large compared to the string scale. Also, the species number get a certain logarithmic correction factor. The species entropy, nevertheless, is still given by the number of species. The number of species is given by this expression. And finally, the species energy, where we sum up in some particular way the entire string tower up to the scale, can be derived in this way. And again, we see that there is some certain, now not constant proportionality constant gamma, which relates the species energy, the species scale. But this gamma now, due to this expression, depends on lambda species itself. So if we now ask ourselves, are the thermodynamic relations for the string tower satisfied? One can say, well, not quite, but perhaps almost. Or in other words, the thermodynamic black hole relations are satisfied only up to multiplicative logarithmic corrections. So they look like thermal black hole laws, but in a way only similar to them. I think the reason for this little bit peculiar behavior of the string tower is indeed that the species scale is now not equal to the string scale, but it is bigger. And again, if you would ask the question, what is the relevant UV cutoff of the theory, it is natural to think about the UV cutoff to be the string scale itself. So we see a subtle difference. That is what I mentioned also before, that the species scale, at least in the way as it is derived here, is not anymore identical to the UV scale. Or in other words, the string tower is heavy compared to lambda UV. And indeed, I think this has to do also with the fact that the string black hole transition, and there was a question about the string black hole transition, is expected to take this particular scale, which is again large compared to the string scale. And this is precisely the transition scale for which a tower of string states, or the string states, or gas of string states turn into a black hole, as it was originally proposed by Horowitz and Polchinski. So you see the string tower is a little bit more subtle than the KK tower, but it's still also, if you are willing to accept this logarithmic correction, it still satisfies the thermodynamic rules of black hole thermodynamics. Yes, please.
Yes, can I ask a question? So the Polchinski-Horowitz scale that you wrote there, if I have then if I'm in dimension bigger than 3, it's much the black hole is much larger than string scale when this happens, right?
Yes, because we measure everything in units of Planck mass, so ms is a number which is smaller than 1.
So it's not so the difference here is a power. It's not like the logarithm you got, right?
This here indeed the difference is a power. It's not a log, and I think admittedly we haven't completely understood the role of the log corrections compared to these power corrections, where the string black hole transition takes place. So I think this is something which one should maybe even understand better.
Thank you.
Peter, can I add something?
Okay.
Can you hear me?
Yes, I do.
Here, as far as I can see, you are not taking into account that some of the species might be charged under some U1, and
Right.
that could change the black hole thermodynamics, right? Is this
That
taken into
is
account?
correct. We have also analyzed black hole thermodynamics for charged species and for charged black holes. I think I will mention this briefly in my summary. So far, indeed, I assume that the species and their corresponding black holes are neutral, and there can be other effects coming from charges from U1s. And in this case, one also has to take into account the weak gravity conjecture. And in fact, I think in nice tests of the emergent string conjecture by Timo and others, precisely these charges also have some interesting effect.
Thanks.
Okay, so this was still top down, but now eventually I like to come to the, I would say, the main result of the work, namely to the bottom up consideration in the last 10 minutes. So how we proceed now from the bottom up? Again, we like to start with a generic species tower, and we like to see how much the tower is constrained by requiring these laws of black hole thermodynamics. So the question in a way is rather simple. We have these conditions, and we like to see how the towers are constrained, whether the towers we have considered so far are the only solutions, or whether there are also other towers possible which satisfy these relations. So if you use my previous definitions, how I've defined the tower, I have the degeneracies in the mass spectrum, and then one can see that these relations in red, they impose some rather, I think, non-trivial relations on the degeneracies dn and on the functions f of n of this form. So I do not show all the details. And at the end of the day, you end up with some nice recursive relations. And these are now the relations which constrain a general tower in order that the black hole laws of thermodynamics are satisfied. Okay, so let us see what kind of results we obtain. As I have said, we like to see now which towers of species satisfy these recursive relations. Of course, if any arbitrary tower would satisfy these relations, the result would be in a way trivial. But as I will show you now in the remaining time, indeed, there are some very interesting constraints, I think, coming out. So let me start with a simple case where we still assume that the degeneracies are one. So this was, for example, the case of the KK tower, which I have discussed before. But now I don't want to assume that we have a KK tower. I start with a general spectrum function f. And if I look at the recursive solution, if I look at the recursive relation, then the solution of this relation is this given by this particular combination of gamma functions, where some particular parameter alpha is appearing. And just to remind you what is alpha, here we have allowed this factor gamma, which allows which is the proportionality between the species energy in lambda species to the 3 minus d. And this alpha is just given by gamma in this way. So this is the solution of the recursive relation. And if you go to large n, you can expand the gamma functions and then indeed you will see that the only allowed tower has this form. It is given by n with the power 1 over p, where p is related to gamma in this way. And if you investigate also some subleading corrections, you will see that the only consistent and allowed towers are those for which gamma is between 1/2 and 1, which means if you translate it into p, p has to be bigger 1. So indeed, this is nothing else than a light KK tower. So from indeed general considerations, we have really derived the Kaluza-Klein tower, namely from general black hole considerations. I like to make one more remark here, that in fact a completely massless tower is excluded, and in this sense cannot build a minimal black hole. For example, a massless tower would be if you have a U-Bahn gauge group U1 to the n of n massless photons, and if you take n to infinity, this kind of tower can never build a minimal black hole, and therefore cannot act as a species which appear in some large distance corner in the modular space. And in this way, it also gives further evidence that in quantum gravity, the rank of allowed gauge groups cannot grow very large. They are constrained by some particular maximum rank. We can refine this discussion a bit more. Namely, we can also allow for some power degeneracy. And I think this also refers to some previous question by Miguel. If you want to generalize the tower a little bit more, we will again see that the only solution now is a generalized KK tower. So also for this case, for a power degeneracy, the spectrum is again polynomial, and the relations between the various parameters work out nicely to show at the end that only a KK tower is a solution of this general ansatz. I can also show you an example of a tower now which is bad or which is not allowed. Namely, if we, for example, assume constant degeneracy, but a tower whose masses grow exponentially, which means that the tower becomes more and more sparse if you go to higher masses. You see that the species scale is given by this expression. The tower energy is given by some certain power of lambda species, and this clearly violates the laws of species thermodynamics, and therefore this is an inconsistent tower which cannot correspond to a minimal black hole. And if you, as I just said, if you like basically to understand the physical reason, is that this tower, because it's exponential, becomes much more and more sparse near the species scale, and therefore the heavy states contribute less to the energy, and I think this is the very reason why this tower becomes inconsistent and cannot build a minimal black hole. Finally, very briefly, I can also come back to string-like spectra. We have also investigated those in more detail. So if the degeneracies are exponential, and we can parameterize them in a little bit more general way, and if for example, the spectra are still polynomial, we get this kind of species scale. Again, you see now the logarithmic correction, which correct the species scale. You also see some correction to the energy. And again, one would perhaps say this is a heavy tower, which looks like a string tower, and indeed satisfies the minimal black hole constraints, but only up to multiplicative corrections. So these are now basically a few examples of towers which we have examined. I can basically summarize our finding in this table, where I have depicted on the one axis the masses, which can be either logarithmic or power-like or exponential, and on the other axis the degeneracies, which can be also logarithmic, power-like, exponential, and constant. And the picture now looks like a traffic light, green, red, and yellow. The green boxes are those towers which are truly allowed. They pass all the thermodynamic tests, and they are all KK-like, namely in the sense that the tower is parametrically lighter than the UV scale, which is precisely what is true for KK states. The red boxes are those which are excluded. They do not pass the thermodynamic tests. And for all these cases, one can say that the spectrum becomes too sparse towards the UV cutoff. And the yellow towers are those which pass the thermodynamic tests, however, with some logarithmic corrections. And they're all string-like. The analysis says that now the bottom-up arguments rule out that this tower is parametrically lighter than the UV scale, but they are otherwise not excluded. And this is precisely what is happening for the string-like towers. So we have this kind of separation. We have the KK towers in green. We have the string-like towers basically in yellow, and the excluded towers in red.
Peter, one question. So
Yes.
How you know that this, for instance, this generalized KK tower, why do you call it like a KK tower? How do you know that cannot appear from other more exotic things? Like, do you have an intuition about what the tower should be like if it comes from extended objects or things like this?
No, I think in this case, these are really still truly extended generalized KK towers, because I can still associate my parameters, alpha, beta, or gamma, which I've introduced to the relevant parameters of compactifications, like in particular, like the number of internal dimensions. So I think they are.
For the generalized tower, you have concrete examples in the string theory that have that structure.
Yes, I think so. Yes.
I see.
Yes, that's correct. Okay, so I think with that, I like to summarize. What I have discussed is that there's a correspondence picture, namely on the one hand, species as particles, and on the other hand, species as minimal black holes. And this correspondence, if you take it serious, puts some strong constraints on the form of the species tower. And all the constraints are basically in agreement, or basically point towards the emergent string conjecture. We would not claim or say that we have proven the emergent string conjecture with that arguments, but I think there are some nice indications for it. But what is, I think, nice is that these thermodynamic conditions on the species are systematic and also rigorous. But in some of the cases, in particular in the cases of the so-called string towers, the interpretation is still very subtle. And therefore, I think it would be also nice to complement these results on the various spectra from a so-called string S-matrix approach. The proposal might be also related to the emergence proposal, where certain quantities like gauge couplings or even gravitational couplings emerge from summing over species again, which means that species possibly also can build space-time geometry. You can use the species for phenomenology. If I have mentioned in the beginning, there's, I think, nowadays a very nice scenario, that is the dark dimension scenario, where species play an important role for dark matter, for supersymmetry breaking, for primordial black holes, for inflation and all that. That is what we also investigated with our collaborators, Luis, Ignatius, Nicolo, and Marco in particular. We are also thinking about, and this is work in progress, how to derive in more detail the species and minimal black holes in their microstates for, in particular, Calabi-Yau compactifications. And in this way, we also have to deal with charged species. So you can see the players, Jose, Matilda, Yishuan and Angel. And we also like to learn more about the species thermodynamics from an entirely particle perspective, namely how the transition from an extensive entropy, which is what you expect in quantum field theory, to an area law really works from a particle perspective, not anymore using the black hole picture. And this is work in progress together with Alvaro, Joachim, and Marco again. So I think there are many interesting things in principle, and also many interesting open questions that one can investigate. And with that, I like basically to close my talk. You have also seen, I think, many nice pictures of various people. And since there's a carnival today, I'd like to show you one more picture, and I'd like to thank you for your attention.